All right, our first speaker for the afternoon session is going to be Lori Ziegelmeyer. She's coming from Macalester College, and she's going to talk to us today about some really nice work on analyzing collective motion with machine learning and topological data analysis. So I'll turn it over to you, Lori.
Great. Thank you, Heather, and thank you, Mason, and all of you who are attending this talk virtually. So to get started, I want to motivate this with applications of biological aggregations. So biological aggregations are groups of organisms such as fish schools or bird flocks or insect swarms, mammal herds that are made up of individual organisms or agents or particles that each individually move, but together might create some collective motion. Now, these individual organisms, they might sense one another via sight or sound or touch or any of the senses. And these senses might encourage them to repel from one another, or they might attract to one another, or they might decide to align with each other. But the idea is that these individual particles might together form some collective motion, and our goal is to understand the behavior of this collective motion through a variety of lenses. Now, if we think of these individual point particles, there might be dozens or hundreds or thousands of individual particles. They each have velocities associated to them, and then these positions and velocities are going to be changing over time. And so this is a lot of data. And what we would want to do is understand how we could actually analyze that data. So a classic way to analyze these biological aggregations is to form some order parameter maybe derived from physics. So for instance, an alignment order parameter would say add up all the velocities and then normalize by these velocities. So imagine we have these individual particles here, each with a position, and the little bar denotes their velocity. And over time, we might, or at this given point, we might say, well, are these particles aligned or are they not? And this alignment order parameter can give a snapshot at this moment in time whether these particles are behaving a certain way. Now, this order parameter tells us something, but it doesn't tell us the full story. So for instance, if we looked at these particles, we see they are all moving in the same direction, so the alignment order parameter would be 1. However, these particles here, even though we might say they're highly aligned just in 2 separate groups, the alignment order parameter is 0. So the alignment order parameter could lead us astray. Now this is for a static moment in time. And what we might want to do is create a time series of the alignment order parameter and see over time what happens to a given set of data. And so if this was the time series that resulted, we could see that the particles are not aligned at early times, and over a period of time, they do appear to align. So that's one method of analyzing this large amount of data. Another method is with topological data analysis. And I know we've had some morning sessions here, but we might have more participants joining us now. And also, if people are joining just for the online session, we can consider a quick overview of topological data analysis. So there's lots of different pipelines that you can use for TDA, and we saw in the morning we could see things like extended persistence or sublevel or super level set persistence. The type of persistence that I'm going to focus on is point cloud data. So we want to envision our data as a point cloud. So for instance, it could be just the position data of your objects, or it could be position velocity data. And for now, we're going to focus on just one snapshot in time. And then from these data, we need to get some notion of similarity, so measure some sort of distance. And what we do is we can build a simplicial complex between proximate points. So a simplicial complex is a topological object that can measure connections between data. And there's a variety of ways to do this. Most commonly, people use something called the Vietoris-Rips complex when they're analyzing data. Now, once we have a simplicial complex, we can determine the topology of it by computing something called homology, which roughly is going to count the number of holes of different dimensions. And what we're going to do is actually vary the proximity parameter that we use to build our simplicial complex across different scales. And this is something called persistent homology. Okay, and so sort of a classic picture is we begin with some data. We think of growing some epsilon balls. Whenever 2 points are pairwise within epsilon, we create an edge between them. Whenever 3 points are pairwise within epsilon, we create a triangle, and then higher dimensional geometric objects can be formed as well. And what we do is we track the different topological features. So some topological features are the number of connected components. So at this early moment in the proximity scale, we see that we have just 7 isolated points. At this later proximity scale, we would have 6 connected components because these two have merged. At this later time, we only have 2 connected components, and we also notice another topological feature in this hole that has formed here. So this can be encoded in something called a barcode, and the way to read a barcode is we have our proximity scale along the x-axis here. So as we're growing these epsilon balls, our simplicial complexes are going to change. And what we're going to do is track how these change. So the idea is that at early scales, we have a distinct bar for each of the topological features corresponding to connected components. Connections merge, and we lose some of these features, and then we're left with 2 connected components until finally everything will connect into a single component. There's a distinct barcode for each type of hole you're counting. So Betty 0 is the number of features of connected components. Betty 1 is the number of topological loops, and so on. Now, the process for doing so, this works great if we have a static point cloud of data. We can count our number of topological features at various proximity scales, and then this gives us some information about our structure. But if we were to take this data, we could think about sort of losing some information from the barcode and just keeping track of this data on, say, a grid. This is something called a Betty curve, which we saw earlier this morning. So this is the traditional pipeline, but what happens if we have a set of data that's moving in time? So we would like to measure the topology as time evolves. Well, we can just take that vertical Betty curve and do this at each time step. And what we get is a function of 2 variables, our proximity parameter and our simulation time. And we can see that this matrix is going to record the topological information over both scale and time. We can visualize this 2-dimensional function as a contour plot. And we have this really clumsy acronym here, contour realization of computed k-dimensional hole evolution in the Rips complex. It's a mouthful. Basically, so we can just say that it's a Crocker plot to display Betty numbers, but you can never say those things together. So this is joint work with collaborators Chad Topaz and Tom Halverson, and it came out in a 2015 PLOS One paper. Okay, so you can think of this as a matrix or as something useful to analyze your data over both time and scale. So Crockers are actually great for exploring your data. So for this talk, I'm going to focus on one particular dynamical system model, the Dorsonia model. It's a very seminal model which has been cited over 500 times in the literature. It describes motion of individual interacting point particles in an unbounded plane in continuous time. So if we have indistinct particles, and we can see that each individual particle will follow these ordinary differential equations, where the first differential equation says the time derivative of position x is our velocity v. Okay. The second equation is Newton's law. So it says mass times acceleration is a sum of forces, where these three different forces are an self-propulsion force, a friction force, and then there's a social interaction force. And the social interaction force can be written in terms of this Morse type potential, okay, where we have a repulsion term and we have an attraction term. So the way to understand this is that for a given particle, as the distance progresses away from this, we can see that the repulsion is going to decay in space. And we're going to have both a parameter of repulsion strength, which is denoted as CR, and repulsion length, which is denoted as LR. Okay. Similarly, we'll have attraction. We see these are signed oppositely, so we'll have an attraction strength and an attraction length scale. So the way to think about this is perhaps over really small scales. If individual particles are really close to one another, they want their personal space or their social distance, and so they're going to repel away from each other for some length scale. Okay. Once they're beyond some length scale, maybe they want to come closer together and attract to one another. And so that would be a length scale of attraction. Now these equations can be non-dimensionalized, and we are left with 4 parameters essentially. So our self-propulsion, our friction, and then the ratios of the repulsion attraction strength and the length scales ratio. Okay, so this Darsonia model is really interesting because it exhibits interesting paradigmatic behaviors. And this is what we're going to explore in our analysis today. So here is one particular parameter set, and we see that we have snapshots of an early time, a middle time, and a late time. And what we have here is individual particles that are essentially just randomly distributed, and they have random velocities at early time. And over time, we see that some structure begins to emerge. And the structure is called a double mill, where we see that we have some particles rotating clockwise, and then we have a minority of particles moving counterclockwise. Okay, and then as time progresses, that becomes even more pronounced. So what we want to do is actually use order parameters and topology to understand that particular simulation from the Darsonia model. And so the order parameters that are commonly used for this model is polarization. So think of polarization as similar to alignment. So are the particles moving in the same direction? If they are, then that would be a high polarization. If they're not, or they're moving in opposite directions, that would result in low polarization. Okay. The other, another order parameter is angular momentum. And so what does this say? It says, are the particles rotating? And in particular, are they rotating in the same direction? So these particles would all be rotating clockwise, so we would have high angular momentum here. Whereas in this instance, it's only medium angular momentum because the particles, yes, are moving in a circle, but some are moving in the opposite direction. And then this would also be low angular momentum because no, they're not moving in a circle. Now, there's also something called absolute angular momentum, where we take the absolute value of the numerator, and this says just, are the particles rotating? We don't care which direction they're rotating, are they just rotating at all? And then finally, we have average distance to nearest neighbor. And so if the particles are spread out, this would be high. If they're clumped together, this would be low. Okay, so what we've done is taken that particular snapshot of the Dorsonia or simulation and analyzed it with order parameters and with topology. So there's a lot on this slide, so I'll go through and describe it carefully. So the key thing is here we have our polarization in red, and these particles don't align. So the polarization is small for the duration of the simulation. Our angular momentum we see over time goes quite high, but we notice that it's not actually 1, and that's because there's a minority of particles that are moving the opposite direction. And so absolute angular momentum can actually capture that all of the particles are moving in a circle. And because there's a difference between absolute angular momentum and angular momentum, we can see that there is this double mill structure. Now, I will say these order parameters are often derived after seeing some collective behavior and then wanting to find some way to measure it. In contrast, in topology, we just take the structure of the data and we don't actually look at or we don't use a priori information about the data to define our measure. So here, this is our dimension 0 Crocker plot, so measuring connected components, and this is our dimension 1 Crocker plot comparing topological circles. Okay, so the way to read this is above some proximity scale, we have only one connected component. Below, in this region, there are lots of connected components which we interpret as noise. And over time, we see this quite jaggedy contour plot. So there's a periodic or sporadic coagulation and fragmentation of features. So in our dimension 1 Crocker plot, we see some actually interesting structure emerge. So after about maybe simulation time 20, we see some structure emerging here. And what these correspond to is 2 topological circles in this region and 1 topological circle in this region. And notice that these persist both in simulation time and proximity scale. And so I claim that this actually reveals that we have a double mill structure because these data are position velocity data that are in 4-dimensional space, and we would actually have our circle going one way and our circle going the other way, corresponding to the 2 circles. Now, they merge at the scale of our radius of this double mill. And I claim that points 1 and 3 are actually closer together in this 4-dimensional space than 2 and 3. Okay, so how are we going to use this to do some parameter identification? So this is our main goal. So commonly, there is a forward problem of we assign some parameters, feed them into some sort of agent-based model, and then we get out our collective behavior. But in this project, we're actually going to do more of an inverse problem. So given some collective behavior, can we use some feature vector that we can feed into machine learning algorithms to infer individual parameters and also understand what types of behaviors we're seeing? So our goal is to say, so what is an informative way to summarize this collective behavior for these various machine learning techniques? Okay. Now, as I mentioned, the Dorsonia model has a variety of really interesting patterns. So if we vary C and L, the ratios of the strength and length scales here, we can get structures such as a single mill, a double ring, collective swarm, and escape. So a single mill, all the particles are going in one direction. Double mill, most particles are going in one direction, a few might be going the other. Double ring, they're all closely aligned to a circle. A collective swarm, they are essentially really close together, and they might be rotating in some direction, and then there's an escape. So the particles essentially just go off into space. And there's various types of escapes, as I've included in this bottom right image. Now, there are these 7 phenotypes associated to various parameters, and we chose 25 different parameter sets, 5 each for C and L. Okay, so our pipeline is that what we do is we take each of these 25 parameter sets and we get 100 realizations where we've changed our initial conditions for our position and velocity. And then what we do is take these simulations and feed them into either order parameters, so we get a time series of the order parameters, or we feed it into topology and we get these Crocker matrices. From each of these, we can get a vector, and these vectors can be fed into machine learning algorithms where we would hope to predict parameters and patterns. So here's just a few of the different phenotypes. Maybe we'll focus on, say, the double ring. And in this plot, we see our order parameters and then our Betty 0 and Betty 1 Crocker plots. And so just a couple of things to point out. We see that our polarization is essentially quite low because these particles don't align. Our angular momentum is high, but not as high as our absolute angular momentum because some particles are moving counter to the majority. And then we see that our particles are fairly close. Now, we also have our dimension 0 Crocker plot. So over time, things get really connected together at some scale. And then also we see our 2 topological circles that persist both for a large amount of scale and time. Now, once we have these feature vectors, we can feed them into machine learning algorithms. And we use 2 approaches. One is an unsupervised approach, k-metroids, and then another supervised approach, support vector machines. Okay, so in k-metroids, we defined a k equals 25 clusters because we had 25 different parameters where each of the metroid is going to minimize the sum of the pairwise distances. And then we assess accuracy based on is a simulation that's assigned to a cluster of a particular metroid, does it actually have the correct parameter or phenotype? We also did support vector machines where we use some of our training data to find hyperplanes that divide simulations according to parameters. And we did a 5-fold cross-validation where we exclude some of our test data, and then our accuracy is based on any simulation that's excluded, or that is our out-of-sample simulations over the total number of out-of-sample simulations. Okay. When we did the unsupervised classification, we got the following results. So let's focus first on parameter accuracy, and we see that this is a quite difficult problem. So we consider the time series or the concatenation of all of these. And we see the values are quite low, whereas with TDA, they're a bit higher. I'll mention we used time-delayed position instead of incorporating velocity in our TDA data. Now, it turns out when you just look at phenotypes, the problem becomes much easier. And this is more easily understood by looking at confusion matrices of our order parameters and our position Crockers and our time-delayed Crockers. And so the red boxes indicate different phenotypes. And we see that even if things are misclassified versus all of the different parameters, they roughly fall within the same phenotype. Okay, and it seems that single mills and collective swarming are the most difficult for the order parameters, whereas only the collective swarming is pretty difficult for the Crockers. SVM, we see the accuracy is improved. So this is a supervised learning or classification problem. And so we see that our accuracy is greatly improved. Now, one thing I should mention is that the dimension of these time series and these Crockers are greatly different. And so you might say this is not really a fair comparison. So what we did is we used PCA to actually reduce the dimension of our feature vectors from, so 87 in the case of the order parameters down to 3. And then we also did the same for the Crockers, the topological information. And you'll see that even reduced to 87 dimensional, we have a higher accuracy with the TDA than with the order parameters. And interestingly, in the low dimensional limit of dimension, we still have quite high accuracy. And then just you can visualize these results in a plot such as this, which has the individual simulations, and we see that we really have very few simulations that are misclassified. So in conclusion, Crockers are a way to understand topological properties of time-varying systems, and they can be combined with machine learning and statistical tools, and they can identify global behaviors, parameter identification, or we've also done a paper where they can be used for model selection. Okay, and I just want to thank my wonderful collaborators. I mentioned Tom and Chad. The bulk of this talk was work that I did with a group of wonderful researchers through a mathematics research community. So if you don't know of these, I encourage you to look into these MRCs. They're great opportunities. So thank you.
Thank you, Lori. All right, if you have questions, I know some people have joined us since I last made this announcement. So if you have questions, please send them in the chat to either Mason or myself, and we can call on you so you can ask your question to Lori.
Yeah, so Corey Brown is pinging me to say he has a question. So why don't you unmute yourself and ask that?
Hi. Great talk. As I mentioned earlier in the last talk, I'm pretty new to topological data analysis. I actually saw Chad give a talk at SIAM Dynamical Systems at Snowbird. It was a wonderful talk. I work in the Koopman data-driven dynamical systems realm, and I'm interested in this intersection with time-varying network analysis, and this collective motion behavioral analysis is a nice application. What was I going to mention? What I think might be nice with these topological characterizations is for time-varying data like this is it might provide a nice constraint for data-driven dynamical systems people in terms of what sort of properties an invariant manifold swarm might be moving on or something like that might help constraining dynamical characterizations or vice versa. So it'd be interesting to find some intersections in these domains. I don't know if you have any comments, but there wasn't really a question, I guess.
Yeah, I think that sounds certainly interesting. And I should mention that Crocker plots are just one tool that can use topology to analyze time-varying system. It's a nice, really simple tool. There's some other more complex tools by like Woojin Kim, and then Corcoran and collaborators also have something that uses zigzag persistence and persistence landscapes. So there's lots of interesting topology tools out there to analyze these sorts of data.
Thanks.
I have a few questions in my chat. The first one's from Ambrose, so maybe Ambrose can go ahead and unmute and ask his question.
Hi, Lori, thanks for a fantastic talk, and these are very interesting results. I just want to go to slide 20. I think it's one of the tables of results, and I seem to notice that for some cases that for parameter accuracy, having the Betty ones, including the Betty ones and Betty zeros, doesn't seem to improve the accuracy by as much as you see in the phenotype accuracy. Do you have any intuition why that is the case?
Yeah, we thought a little bit about this, and I think, these are very high dimensional features. So in the next slide, I show the dimension. So 200 by 86 dimensional features. And so the way I can think of this is it's a high dimensional feature that's not contributing that much. So it actually allows for more confusion in the classifier than the added benefit is essentially what I would guess is happening here.
Okay, thank you.
Okay, we have one last quick question, and then I think we'll probably want to get our next speaker set up. This is a question from Wenwen Lee, who asked if I could ask this question by proxy. The question is there any place we can apply TDA methods in the machine learning other than labeling the data?
Other than labeling the data. So, for instance, this, I'm not sure I quite understand the question. So it is true that we do have labeled data either for the parameter or the phenotype in this, but k-metroids is an unclassified approach. And of course, any machine learning algorithm where we don't have labeled data, if we have some subset that is labeled and then we get, say, a new sample, we could see where that is classified with the already labeled data. I'm not sure if that answers your question. I'd be happy to talk about it more offline.
And it looks like we might even have some questions we won't have time to get to. So we encourage you to reach out to Lori and continue these discussions, because I think there's a lot of really good discussions to be had here.
Yes,
but, yeah.
Thank you.
So in the interest of time, let's thank Lori again.